Okay, so good morning, everybody. So today we are going to do the part concerning estimation theory. In few words, okay, so what we are going to do is in some sense a generalization of what we have done previously, okay, in the previous chapter. So we are going to have a parameter or set of parameter of interest, and the idea, okay, is to be able to approximate this parameter, okay, that may be a vectorial parameter using observations of particular random variable of particular distribution. And the idea here is to have a systematic way in order to be able to build such approximations and to have a way to compare them and even to have a criteria that will allow me to say that an estimator will be the best possible with the tools involved in this course, okay? And particularly, we will also have a way to find, if it exists, this best, let's say, approximation. Okay, so it's what we are going to do today. Okay, so I split my screen. Okay, so concerning estimations, okay. And my problem is the following, okay? So I consider a random variable that may be, as always in this course, a discrete one or a continuous one, okay, with a distribution that depends on a parameter, okay? Theta may be a number or it may be a vector, okay? I may have several parameters of interest, okay? And a priori, I don't know this theta, okay? And what I want to do, as I have said, okay, is from observations, so from a capital N sample of my initial distribution, and I will denote this sample x1, x2, x capital N, okay? And I remind you that what is a sample? Okay, it's something where the random variables are independent and with the same distribution. And here, this distribution depends on my parameter theta that I don't know, and I want to approximate, okay? So I want to approximate this theta. And in order to approximate theta, it's a notion that I have previously introduced, okay, in the previous chapter, but let me remind it, okay? What is an estimator? It's the definition B1, okay? An estimator is just a regular function of the observations, okay? So I will denote it in this section by theta hat, okay? Theta being my parameter of interest. Theta hat will be my approximation that depend on my set of observation x1, x2, xn, okay? And in the following, okay, in general, in order to make the notation lighter, I will denote by theta hat, in fact, theta hat of x1, x2, x capital N, okay, omitting the fact that my estimator depend on the observation because, okay, it is the case from the definition. And what I want to do, okay, in this course is to have ways in order to obtain systematically such an estimator, such a theta hat, okay, and I want it with good properties. So I mean properties, okay, so we are going to review several definitions in order to have in mind what may be good properties for estimator. So I repeat that once again, it's something we have previously seen in the part concerning sampling, okay? So let's see this. So what may be these good properties? First property, okay, is the fact that we want estimator that are unbiased. Unbiased means that, okay, so keep in mind that my theta hat here, I denote theta hat as theta hat a function of my capital N observation here. Theta hat, I want it to be an approximation of theta, okay? And I say that my estimator is unbiased is the expectation of theta hat is equal to the parameter of interest, that is theta, okay? It's what I call unbiased, okay? And I remind you that in fact, the difference between the expectation of my estimator and the parameter of interest, it's what I have called in the previous session, the bias of an estimator. So for a good estimator, I want it to be equal to 0. And you will see that in this course, okay, the objective will be able to find unbiased estimator because I will have a criteria in order to compare them. Okay, so in average, let's say an unbiased estimator is equal to the parameter of interest, okay? But the fact is, it may exist, okay, several unbiased estimator for a parameter theta. It's possible to have this situation. I will give you an example just after in a few minutes, okay? So if I have several unbiased estimator, a natural question is how to compare them. How to compare them, okay? And in order to compare them, okay, we have introduced the mean square error, okay? So the mean square error that is defined this way. So keep in mind that I have introduced a distance in L2 that associate to two random variables. Okay, so it's something with values in R plus. The expectation of the square of the difference to the power 1/2 in order to obtain a distance. Okay, this is a distance. I have proved it. It was a consequence of the Cauchy-Schwarz inequality. Okay, and in order to compute or to compare different estimators, we are going to compare the distance between, okay, so we are going to handle the distance between an estimator and the parameter of interest, and we want it minimal, if possible. If possible, it's not always the case, but if possible, I want to minimize this, okay? So what is this one? It's the expectation of the square of the difference to the power 1/2. And of course, if I want to make this quantity minimal, okay, I can remove the square root here because, okay, the square root is a strictly positive mapping. So if I put it or not, it changes nothing in my optimization problem. Okay, so we are interested in the expectation of theta at minus theta square. And this is this quantity that I call the mean square error. Mean square error. Okay, so mean because I have an expectation, square because I have a square, mean square, I have a square here, okay, and error because, okay, it measures in some sense the distance between theta hat and theta. It's the square of a distance. In a computation we have already seen together, okay, I see that I can express this quantity in the following way. The expectation of the square of the difference, and I can introduce in this expression theta hat minus the expectation of theta hat, but if I subtract it, I have to add it, okay, in order to change nothing in my relation here, minus theta square, so I have this, and I can develop this square. If I develop this square, okay, so I will regroup the term this way, and if I do this job, okay, I obtain what? I obtain the expectation of the square of this one here, that is the variance of theta hat, by definition, plus what? Plus the square of this, the expectation of the square of this quantity, but this quantity here, I have a number. It's not a random variable, it's a number. Theta is is a number in this situation here, okay? And theta hat here, the expectation of theta hat is also a number. So I have here simply the expectation of theta hat minus theta square. And I remark here that I have what? I have the square of the bias here, because this quantity is the bias. Okay, so I have the square of the bias plus the double product. And what is this double product? It is the expectation of theta hat minus the expectation of theta hat multiplied by a number that is equal to this one. And I see easily that this quantity here, this one, is equal to 0. That's why I can express, as it is written in this formula, I can express my mean square error here. I can express my mean square error as the sum of the variance of my estimator plus square of the bias. And in particular, as it is written here, when the bias is equal to 0, so unbiased mean bias equal to 0. If the bias is equal to 0 here, then the mean square error is simply this term, that is the variance of my estimator. So when you have unbiased estimator, if you want to compute the mean square error related to my approximation process, okay, I just have to compute the variance of this estimator. And if I want to compare two unbiased estimator, it is sufficient for me to compare their variances, okay? Because the mean square error is equal to the variances in this case. Okay, so just introduce in relation with what I have said here some definitions, okay? So if I start with an estimator that is unbiased, okay, we say that this estimator is efficient if its variance is minimal. It's the first definition. So efficient mean variance minimal. And if I come back to what I have said previously, in the case of an unbiased estimator, the mean square error is the variance. I want to minimize the mean square error, okay, in order to compare estimators. The variance in this case is the mean square error. So in fact, I want to minimize the variance. And if it's possible for me to minimize this variance, I will call the corresponding estimator as efficient, okay? So what we want, it's something, okay, to be able to find such a theta hat, to find unbiased estimator, okay, that are efficient depending on the problem of interest, okay? So we say that theta hat is BU, B-U-E, if it is unbiased and efficient, okay? So BU means best unbiased estimator. Is the meaning of BU. Among the family of the unbiased estimator, it is the best. In which sense? But in the sense that it is efficient, that is, it is with a minimal variance, that is a minimal mean square error. Okay, so it's what we want, in fact. Okay, I expect in this course to be able to find BU estimator. Just another definition that will be more marginal, okay, in our setting, but we say that theta hat is blue. So I add a L here, okay, I add a L. And why I have this L here is just because, okay, if I have a best unbiased estimator that fulfill L, that is linear in the observation, okay, we call it blue, okay, we call it blue. So a blue estimator is an estimator, okay, that is unbiased, linear, and that is the best among, okay, the linear unbiased estimator, that is the one that has the minimum variance. But what we are going to be interested in this course mainly is to find view estimators that are ones that are unbiased and efficient. Efficient meaning that the variance, so the mean square error, is minimal. Okay, so it's what we are going to have in mind here in our situation. Okay, so what we have done, so we have already worked on this kind of problem, in fact. Okay, in the previous session, okay, we have seen the sample mean. And what was the sample mean? It was a way to approximate the expectation of a sample based on n observations. So here I have IID random variables in L2. I want to approximate the expectation, and we have introduced the sample variance here. I remind you that the sample variance in this situation is just xn over line is equal to 1 over n, the sum from I equal to 1 to n of the xi here. Okay, so it's the sample variance, this one. We have already seen together that the sample variance is an unbiased estimator of mu, that is the expectation. So in some sense, the average, the sample mean here, is an unbiased estimator of mu through this relation here. And we have a way to compute the mean square error in this situation, because we see easily that the variance of this unbiased estimator, that is none other than its mean square error, okay, is the variance of x1 here, so x1, not an x1 here, variance of x1, let's say, over n, okay? So the mean square error is given by this expression here, okay? So it's what we have done for the mean, the expectation, okay? We have done the same job for the variance. So in the variance, we have introduced, in fact, 3 estimators. So the first one, that was the ideal sample variance. So we have here random variables in L4. We want to approximate sigma square, that is the variance of each of them, okay? And using the previous analogy, okay, since I can write the variance as an expectation, I define the ideal sample variance this way, okay, where mu, I remind you that mu here, mu is equal to the expectation of each of them. That is the expectation of x1 because they are independent and identically distributed. We have seen together that this is an unbiased estimator of the variance because the expectation of sigma n tilde square is equal to sigma square. So I have something that is unbiased. So if I want to compute the mean square error, I have simply to compute the variance. And I have done the computation in this case. It is mu4 minus sigma 4 over n here, where mu4 is this quantity. Okay, it's the force-centered moment as introduced in the previous session. So a priori here I have the same kind of answer than in the case of the expectation. The only problem I have here is this one. In my approximation, if I want to compute explicitly this one from the observation, I need to know mu. Mu being the expectation of my sample. But in general, okay, mu is unknown. So it means that in general, sigma n tilde can't be computed in practice. Okay, you can compute it only in the case where mu is known. Okay, so if you know mu from the statement, okay, you can use it. But if you don't know, you have a quantity that you won't be able to compute. Okay, and we have seen how to overcome this problem here. What happens if we don't know mu? That is, okay, the general case, the generic case here. But when mu is unknown, okay, what we are going to do, the idea is to replace mu by an estimator of mu, and the estimator we have seen previously was the sample mean. So to overcome this problem, okay, we replace in this formula mu by xn over line. So it's what I have defined as the sample variance here. Okay, so you have the sample variance. That was just the analogous of the previous one, where I have replaced here mu was replaced by xn over line. If I have mu instead of xn over line here, I have the ideal sample variance. If I replace mu by xn over line, I obtain the sample variance, and the interest of this quantity here is the fact that I can compute it explicitly from my observations. Okay, from the x1, x2, xn, I can compute it because I don't need to know mu. Okay. We have done the computation of the expectation of this estimator in the previous session, and we have seen together that unfortunately, okay, the sample variance is biased. Sample variance is biased because the expectation of sigma n square is different from sigma square. And we obtain this value for the expectation of sigma n square. So when n is large, okay, we are not very far from sigma square, because when n is large, this quantity is almost 1, but it's almost 1, but it is not 1, okay? So I have a natural estimator for the variance, but unfortunately, this estimator is biased, okay? But since we have this expression for the expectation of my sample variance, it is very easy to correct it in order to obtain an estimator that will be unbiased. It's what we call, okay, the corrected sample variance, that it is the one we use in general in order to approximate a variance. And how to obtain it, okay, simply when I see this expression here, I see that when I multiply by n and divide by n minus 1, I obtain sigma square as an expectation in this relation. So if I multiply this relation by n and divide it by n minus 1, I obtain on the right part, okay, sigma square. But it's exactly what we are going to do. We are going to correct the sample variance, multiply it by n and divide it by n minus 1 in order to obtain something that will be this estimator, the corrected sample variance that will fulfill the expectation of Sn square is by construction sigma square. So you have something that is unbiased. You have something that is unbiased here. Okay, and I remind you that if I apply this formula with sigma n squared that is given by this expression here, I obtain simply that Sn square. So it's not very far from this one. Huh? It's the sum from I equal to 1 to n of xi minus xn over line square. But instead of dividing by 1 over n, I divide by 1 over n minus 1 in order to make this corrected sample variance an unbiased estimator of the variance. Okay, so I have an unbiased estimator of the variance. If I want to control its mean square error, okay, I have simply to control its variance. And we have admitted together in the previous chapter that I am able to know what is the variance of the corrected sample variance, and the variance of the corrected sample variance is given by this expression here, this one, and sigma square is just, I remind you, the variance of x1. So here I have just the variance square, sigma 4, okay, and mu 4, it is just the force centered moment, this one. Okay, and I close the bracket here. So if I want to compute this variance, okay, I will plug inside the variance of x1 and I plug here the variance of mu4, okay, the variance mu4. And in general, okay, for some particular distribution, you are going to be able to compute it as we are going to see in a few minutes in an example with the Poisson distribution. And what we have proved together is that, okay, if you have a look on the variance, I have two unbiased estimators. The ideal one, that is the ideal sample variance, but that necessitates the knowledge of mu here. And a more practical one, that is the corrected sample variance, defined this way. Both of them are unbiased, okay? And if I want to compare them through the mean square error criteria, I see that the mean square error of the corrected sample variance is, of course, strictly greater than the mean square error of the ideal sample variance, okay, for sure. But keep in mind that this one, okay, we can't use it in general in practice, okay, because I don't know mu. So I have this relation, okay, but the advantage of this one is that I can compute it from observation, while this one can't be computed from observations, okay? So I have this relation, but, okay, I can use it, I can't use it, this one in general, okay? So it's also something I've already said is that, okay, what we have done for the expectation and what we have done, okay, for the variance is just a special case of a general methodology in order to obtain estimators of moments, okay, that is called the method of moments. So it's a proposition we have already seen together. So we have this one, okay. So if you have a quantity, okay, that is related to the moments of the distribution of x. So by moments, okay, what I call moment is just, okay, the expectation of, okay, x to the power r, let's say. Okay, so for r equal to 1, you have the expectation. For r equal to the expectation of the square, and so on, okay? If I want to approximate this quantity here, I have what we called the r sample moment. Why? Because keep in mind that this is just the expectation of x to the power r. We know together that the expectation of x can be approximated by the sample variance, that is 1 over n sum from I equal to n of the xi here. And of course, a natural way to approximate x to the power r is just put xi to the power r here. That is exactly what I have here, okay? So it's exactly the analogous of what we have done in the case of the expectation that I can generalize very easily to the case of more general moments of the distribution. So if I want to approximate the expectation of x square, I do the average of the square of the observation. If I want to approximate the expectation of x to the power 3, I have to do the average of the observation to the power 3 and so on, okay? And what I have defined as the sample mean here is just the M1 with my notation here. We have also done the job for this kind of quantity here. So in this part here, I am not interested by the expectation of x to the power r, but we are interested by what we call the r-centered moment, okay? That is, in fact, to be interested in this one to the power r, okay? In the case where r is equal to 2, you obtain simply the variance, okay, of capital X here. And by analogy with what I have done previously, I said that in fact I have two expectations here, this one and this one. So I will approximate this expectation here by the sample mean, and I will approximate the expectation of this random variable to the power r by the r sample moment that give me as an approximation this quantity. And just remind that for r equal to 2, you have just, okay, what I have called the sample variance, okay? So I have I have this one. Okay, so maybe just have a look on a little example. Okay, that is if I remind, okay, the exercise 2 of the list of exercise related here. So I just reduce my slides here. Okay, in fact, here it's the exercise 2 of the list B. That is the list related to this one. Okay. So what I have in my situation, so here, okay, you have an n sample in this exercise. An n sample of Poisson distribution of parameter lambda. Okay, and you have your lambda that is strictly positive. Okay, it's the statement of this exercise. Okay. So I know that the parameter lambda, okay, that is the parameter of the Poisson distribution, okay, but lambda is related to the expectation and to the variance of, okay, a Poisson random variable. I know that if x follows a Poisson of parameter lambda, I know that the expectation of x is equal to lambda, and I know that the variance of x is equal to lambda. Okay, I have these two equalities we have seen together in the part concerning discrete random variables. And so we have two natural estimators. So two natural estimators for lambda. What are they? But I use this. Okay, I can approximate lambda considered as an expectation by the sample mean. And I can approximate it by the one that I will use in general for the variance, that is a corrected sample variance. Corrected sample, excuse me, variance. I know that these two estimators are unbiased estimator. So in this case, mean square errors are just variance of the estimators. Okay, I am in this situation. So if I want to compare these two, okay, if I want to compare these two, then I just have to compare their variances. So I have the variance of xn over line and the variance of Sn squared to compute. And I know them because it's something that I have reminded before. So here, for the sample mean, I know that the variance of the sample mean is just the variance of my sample, of each element of my sample divided by n. Okay, so here it is just lambda over n. This one, that is just the variance of x or x1 over n here. For the corrected sample variance, we have a formula that is a little bit more complicated. That is this one. Okay. It is this formula for the variance of the corrected sample variance with sigma square that is equal to variance and mu4 that is the force-centered moment. Okay. So here, okay, I just remind, so in the statement of the exercise, so for the variance of x, I know it. It is lambda, the variance of a Poisson. In the statement of the exercise, they give you, okay, the following, that the expectation of x minus the expectation of x to the power 4 here, in the case of a Poisson, is given by this expression that is given by the statement. Okay, it is lambda minus 3, okay, or plus, excuse me, plus 3 lambda square. I have this one here. Okay, the force centered moment, okay, is given by this one, and it's what I have called. So here you have sigma square. In the case here you have mu4. Okay, so if I copy the formula for the variance here, what I have, so let's come back to this expression. I have 2 sigma 4 over n minus 1. So 2 sigma 4 over n minus 1 plus mu 4 minus 3 sigma 4 over n plus mu 4 minus 3 sigma 4 over n. And if I plug inside here using this, I obtain what? I obtain for this expression, okay, 2 lambda square over n minus 1 plus, so mu 4 minus 3 sigma 4, that is just equal to lambda. In fact, using this, I have just lambda over n. Okay, so I have this quantity. Okay, so I have this one, and I can remark that if I want to compare these two unbiased estimator, I have to compare their variances. The variance of the sample mean is given by this expression here. The variance of the corrected sample variance is given by this expression, but I see that the second variance is equal to what? To the first one, plus a term here. That is a term that is strictly positive. And the meaning of this one means that if I want to approximate the lambda parameter of a Poisson distribution, I have two natural estimators that are the sample mean and the corrected sample variance, both of them being unbiased. And the best of the two is, in this case, the sample mean, because the variance of the sample mean is the smallest one, okay? And so in this particular situation, if you have the choice, okay, use the sample means instead of the corrected sample variance, because you will obtain, okay, an estimator with a mean square error that is smaller. But here you see that in a practical situation, if I have several estimators, okay, let's say 2, 3, 4, or 5, okay, I can compare them if they are unbiased, okay, computing them, their variances, okay? So here I am able to say that the sample mean is better than the corrected sample variance in order to approximate the lambda parameter of a Poisson, but I am not able to say if the sample mean is the best among all of the unbiased estimator. I am able to do pairwise comparison here, doing explicit computations, but I am not able a priori to test, okay, the absolute quality of the estimator, that is to say it is the best among all the possible candidates, okay? And in the following, okay, it's what we are going to try to do. So first we are going to see how to obtain estimator in the case where we are not in the framework of method of moments, that is in the case where my quantity of interest are not a priori expectation variances or, okay, are the moments of order R or R centered moments, something like this, okay, because with the method of moments I have ways to approximate, but if my parameter theta is something that I don't know a priori as expectation of the variance of someone, okay, I can't use this methodology. So we are going to see what happened in this situation, and we are going to see that using this new way to obtain estimator, we are going to be able to have a criteria in order to test the quality of these estimators. Okay, so it's what we are going to do now. Okay, so we are going to define, in fact, what we call the likelihood problem, the maximum likelihood estimator, and to see that in this situation we have criteria in order to do the job we want to do. Okay, so after this big introduction, okay, let's come back to, in fact, the real new part of this course. Okay, that is what we call, excuse me, so this one I can erase because I have already said everything concerning this slide here. Okay, and it's what we called the likelihood problem here. Okay, so what I know. So the starting point of this problem is the following one. So you start with a random variable, okay, that is capital X here with my notation. And the only thing you know, okay, is that the distribution of this random variable, okay, belongs to a known family. What I call a known family. A known family in my course is, okay, suppose that this distribution is discrete, but it will be among the classical discrete distribution we have seen together that are uniform, Poisson, okay, binomial, Bernoulli, and geometric, let's say. Okay, so in the discrete case, it will be this one. Okay, I don't know precisely what is the distribution, but I know that the distribution of X is a uniform, or a Poisson, or a geometric, or a binomial, or a Bernoulli, and so on. Okay, in the same way, if we are in the continuous case, I will know if capital X is a Gaussian, or if capital X is uniform, or if capital X is an exponential, or if capital X is a chi-square, or if capital X is a gamma, okay, or if capital X is an F distribution, or if capital X is the student distribution. So the classical distribution I have in my course. So the only problem is that I know the family, okay, of interest, but I don't know precisely what is the distribution of my random variable. So let's take two examples here, one in the discrete and the other one in the continuous case. So suppose that you know that X, okay, has a Poisson distribution. So I know from definition that if I am a Poisson distribution of parameter theta, my probability mass function is given by this one, okay? But for the moment, you don't know what is theta. You don't know what is theta in this situation, okay? The only you know is that X follows a Poisson of parameter theta. In the same way, I can take another example that is, okay, I know that the distribution of capital X belongs to the exponential family, okay, but I don't know what is the parameter of this exponential distribution. So the only thing I can say is that, okay, my capital X, okay, has a density function that fulfills, okay, this property, okay? So two examples of such a situation. So what you know when you start in the likelihood problem, you know first the set of the possible values for the parameter theta. So we are going to suppose that even if I don't know theta, so theta is unknown, okay, but I know the set, okay, on which theta, okay, can take values. So we don't know the parameter precisely, okay, but we know the set, if some sense, okay, the set of possible parameters, of possible values, let's say. You know the set of the possible values. So for example, in my two previous example, okay, in the case of a Poisson of parameter theta and in the case of an exponential of parameter theta, okay, so I can see here, example, for my Poisson of parameter theta or my exponential of parameter theta, I know that theta belongs to R plus star, okay? It is the capital theta here, the set of possible values for my parameter. So just a remark, here we are in the case where theta is a number, okay? So I have a set here that is, let's say, a subset of the real numbers, but my parameter theta, okay, can also be a subset of R to the power n. If you are, for example, in the following situation, okay, so suppose that X follows the n mu sigma square. So my parameter of interest here is a parameter of dimension 2, theta, mu sigma square, okay? And I can say that the parameter I don't know theta belongs to what? But the mean may be in R, and the variance, okay, I will take it in R plus star. Okay, so my set of parameter in this situation is a product of two sets, okay, that is a subset here included in R square. Here I am included in R. Here I am included in R square because, okay, I have here it's R to the power 1 because I have a single parameter. Here I have two parameters, so that's why I have the 2 here, okay? So the set of the possible values that is included, okay, let's say in R to the power d, d being the dimension of my parameter, d equal to 1 in this case, d equal to 2 in this one, okay? So I know this theta, so this one is known. And it will be for you given by the statement, okay? What I know also, it's the set of distributions, okay, related to my problem. So it means that you will know, we know the family the family of the distribution. So it means that, okay, what is the meaning of this? But typically, if I take my three examples here, in this case here, I know that, okay, my X is a Poisson. So I know all the related probability mass function, okay? Even if I don't know theta, I know this expression for the probability mass function, okay? Even if I don't know theta, it belongs to this family here. In the case of an exponential, I know that X follows an exponential, so I know that it has this density function, even if I don't know the parameter theta. And if I have in the case of my Gaussian here, I know that the density function is this one. Okay, so I know that the density of capital X belongs to this family, even if I don't know precisely mu and sigma square. Okay, so I know the family of the distribution, and it will be given by the statement for you. Okay, but in general, if you are in a real life problem, okay, but the person that wants to model a particular situation will have to choose among a family of distribution, okay, that is the best as possible, okay, for its own problem, okay? So I note it. So a notation that would be important, okay, so theta is the parameter of interest, and I will give a name to theta 0, that is the true parameter. the true one, the one I want to approximate. Of course, I don't know this one, but I just give it a name. I don't know. I want to approximate theta 0. Okay, I know that theta 0 is among this set of possible values. I know that theta 0 is related to a particular family of distribution. Okay, and I just give a name to the true parameter that is theta 0, implying that, in fact, x, okay, has a distribution depending on this theta 0, the true value, okay, that I don't know explicitly and that I want to approximate, but just keep in mind that with my notation, it's exactly what I have written here, okay, that if I want to find the density of capital X, first of all, I know that this density belongs to this family in the continuous case or this family in the discrete one. I know that among all the possible candidates, okay, theta 0 is the true parameter. So with my notation here, the density of X is just this quantity with the true parameter. I repeat, I don't know this parameter, but just say that it is the true one, okay, the real one. And the same that the probability mass function of X in the discrete case, okay, will just be the probability that X is equal to small x, given that the parameter is in fact theta 0. Okay. So I am in this situation. I am in this situation. So I know, I repeat, I know the set of the possible value for my parameter, that is a subset of R to the power D. Okay, so here I have examples for D equal to 1. Here I have an example for D equal to 2. Okay, I know the family of the distribution of capital X. So I know, for example, that if it follows an exponential, a Poisson, a Gaussian, a gamma, and so on and so on. Okay, and I just give a name to the true parameter, the one I am interested in. Okay, that is denoted by theta 0. That is but the parameter of interest, that is the one I want to approximate the best. Okay, so that is this one. And keep in mind that if I start from the observation of a distribution capital X, okay, with an sample, what I will have as a property is that the density of my observation is just the density observed at the true parameter, that is theta 0. Okay, so I have this one. And we are going to see that with this setting, okay, we are going to have some systematic ways in order to approximate my theta 0. Okay, so this is what we call the likelihood problem. Okay, and we are going to see that, in fact, the true parameter theta 0 fulfills a very interesting property. Okay, so I am in this situation. So let's continue. So I am where I am. Okay, I am in this situation. Okay, I said the following. In fact, the true parameters, and it's something that is fundamental here, may be obtained, okay, as the maximum of a mapping related to my density function. So just a remark, because you see here that here, okay, we are going to write the things in the continuous case. Okay, so keep in mind that I have two possible situations. The one where I have a family of density function this way, okay, a family this way, theta belonging to theta. I have here density functions. And in the discrete case, I am in this situation. Instead of having density function, I have probability mass function here. Okay? In order to avoid to consider any time two cases, okay, I will make these two notation coincide. So from now on, okay, this one will be also for a probability mass function. So when I will write this one, it will just mean that in the continuous case, I am really a density function as usual, the one that is positive, continuous, okay, except at a regular subset with an integral equal to 1. And if I am in a discrete case, okay, this, what I call the density, is just the probability mass function, okay? So using this, it allows me to use a single notation, that is this one, in both continuous and discrete cases, okay? So a single notation for the two situations, okay? So here, typically, in what we are going to write here, F will be in the continuous case, the density, and in the discrete case, the probability mass function. And I say that, in fact, theta 0 is the parameter that make maximal this quantity here. So this quantity, that is the expectation of the logarithm of f capital X theta. The one that make this quantity, okay, maximum. And what is this one? Okay, so with my notation, so I will use from now on, okay, an integral notation for these quantities because, okay, of my approximation. If I am in the discrete case, okay, so just maybe let's write it one time. So this one is a priori what, okay? So keep in mind that capital X is my random variable of interest. I know that its density belongs to this one, and I know that the true parameter is denoted by theta 0. So if I want to compute this expectation, if I am in the discrete, in the continuous case, it is just the integral of the logarithm of f x theta multiplied by what? By multiplied, because here inside you have capital X here. So multiply by the density of capital X, and I know that the density of capital X is fx theta 0, okay, dx here. Integral from minus infinity to plus infinity. So here it is in the continuous case. In the continuous case, I have this one. If I am in the discrete case, what I have to compute, if I am in the discrete case, I have no an integral, I have a sum, okay, of what? Over the possible value for capital X. So X belonging to X of omega of what? But the logarithm of f x, that is just, excuse me. Okay, so what we are going to do, I want to make it clear. Okay, so instead of writing here, I will put a star here and I will continue my thing here, equal to what? In the discrete case, it's the sum over the possible value of x of omega of the logarithm of the probability mass function that x is equal to small x associated with the parameter theta. And I have to multiply by what? By the probability mass function of capital X. And the probability mass function of capital X is what happened at theta 0. Okay, so in the case where, okay, I am in the continuous case, I have this integral that becomes a sum as usual in the discrete case. Okay, so just keep in mind that here you have simply the expectation of, you have the expectation of a function of x, in fact. So you use, it's the expectation of a function of capital X, that you can express using the integral of the density being fx theta 0, or the sum of the probability mass function, the probability mass function being this one. So here I can write, okay, the true density. I don't know this true density, but I can write it, the true density, and here the true probability mass function. Okay, and what is nice is that my parameter of interest, my parameter of interest theta 0 here is the one that maximizes this quantity. Okay, it's the one that maximizes this quantity, and it's what we are going to prove just after. Okay, it's the one that maximizes this quantity. And what is more, what you know from the course of optimization is that if I want to find the theta 0, first you have to solve, okay, the first order condition. That is, okay, the Euler condition for my maximum, okay, that is the one that will make the derivative of my objective function equal to 0, and that's why we are going to have this second statement here. Okay, so what I want to prove now, okay, is this proposition B1. And this proposition that will allow me, and it's important, to express my parameter of interest as, okay, the one that maximize a particular objective function. Okay, so I keep the slide here, and maybe this slide I will duplicate it in order to use it later if I need. Okay, so let's do the proof of proposition B1. That is the one, okay, that will allow me, I repeat, to express my parameter of interest as a the result of a maximization program. Okay, so let's define here what I want to maximize. That is the mapping that I want to maximize here. It's phi. Okay, that is a mapping from the set of parameter I know with values into, let's say, R, that associate to any little theta in my set of parameter, but the quantity of interest, that is the expectation of the logarithm of f capital X theta. Keep in mind that X, okay, has a density that is a real density in the continuous case or a probability mass function in the discrete case, that is f of X theta 0. Okay. So I repeat, so we are going to write everything, okay, in the continuous case. Okay, so I write the things, and it's what we are going to do until the end. So we write things as in the continuous case. Everything. In fact, here I will work with integrals, okay, not with sums, okay, but the things will be the same if we do this, okay, and you will see examples, okay, in the exercise. So it means in particular that my function of interest here, okay, as I have said, is just, so it's the expectation of a function of capital X having this density function, so it's the integral minus infinity plus infinity of the logarithm of f x theta multiply, so parentheses if you want here, multiply by what? Multiply by the density of capital X, that is fx theta 0 dx. Okay, and the idea is to write that, okay, to see that in fact this one has a minimum at a point that is none other than theta 0, that is my parameter of interest. Okay, maximum at the parameter of interest, that is theta 0. Okay, so if I want to study the max, okay, I know first that I have to solve the first order condition. So we are going to try to compute the derivative of phi here. Okay, I want to compute it. So the thing that is important from now on is that in this course, okay, and even for the final exam, if you have, okay, so if you are in this situation, if you want to compute the derivative with respect to theta of the integral of a function depending on theta. So something this way. And the same for a sum. I write the things in the case, in the continuous case. So if you want to compute derivative of integrals, you will always use the fact that the derivative of an integral is just the integral of the derivative. You can invert the position between integrals and derivatives here, okay? So you have theorem in mathematics that are called, okay, the Lebesgue type theorem that will allow you to do this very correctly, okay? We have hypotheses in order to do this. In this course, I don't want to enter into too much details, but I will just suppose that you are able to invert. So computing the derivative of an integral, okay, is just the integral of the derivative. Okay, so apply this one. So this one is always true for you. Always true in this course. And typically, this result is that natural because keep in mind that what is an integral? It's the kind of limit of a sum, if I consider the limit of the Riemann sum. And I know that when I have a finite sum, the derivative of the finite sum is the finite sum of the derivative, okay? And let's say that this result tells you that you can pass to the limit in a correct way. In order to pass to the limit in a correct way, a priori, I have to check some hypotheses that we'll consider as always true in this course, okay? So when you will see that I will do this several times to compute derivative of integrals, I will just compute, okay, the integral of the derivative. So let's do the job here, typically for my situation. So if I want to compute the derivative of this quantity with respect to theta here, I have a single theta that is here, and because here you have theta 0. Theta 0 is fixed, and suppose here, I don't know it, but it's theta 0, that is a fixed number that I want to approximate, okay? But that exists by itself. Here I have theta here. So I have the logarithm of a function of theta here. So if I apply my thing here, the derivative of the integral will be the integral of the derivative. So I have to compute the derivative of this quantity here. And I know that the logarithm of u is, I can compute its derivative as u prime over u, the derivative of the logarithm of u. So I can write it this way. So the derivative with respect to theta of this quantity here will be the derivative with respect to theta of f of x theta divided by f of x theta f x theta 0 dx. Okay, so you have here the derivative of phi with respect to theta. Okay, so I have this one. Just a remark, but what we know is that, okay, all these mappings here, depending on x, are density function. So if we have density function, we know that the integral of all these mappings with respect to x are equal to 1. All these mappings are density functions, so they have an integral equal to 1. So if I compute the derivative with respect to theta of this relation here, okay, I obtain that the integral between minus infinity and plus infinity of df x theta with respect to theta. What is this one? Computing the derivative of this one with respect to theta give me this one, and computing the derivative with respect to theta of 1 will give me 0. Okay, so I have this relation here for any theta. If I compute the integral of the derivative with respect to theta of my density functions, I obtain always 0. And so if I combine these two, okay, what I obtain, so maybe let's write it here. So we have that, I repeat, phi prime of theta is equal to what? The integral minus infinity plus infinity d over d theta f x theta divided by f x theta multiplied by the true density that f x theta 0 d of x. Okay, and I have the fact that if I compute this one, d over d theta of f x theta dx is equal to 0. So in particular, okay, so I have these two from what I have done previously, admitting that computing the derivative on integral give me the integral of the derivative. If I compute phi prime at the point theta 0, that is the true parameter, I don't know, but the true one. So I plug theta 0 inside here, and what I obtain. So if I plug theta 0 here and here, I have a simplification between this one and this one, if theta is equal to theta 0, and I obtain simply d over d theta f x of theta 0 dx minus infinity plus infinity, because I repeat, if theta is equal to theta 0 in this expression, here I have simplification between this one and this one. That's why it remains only this one at the parameter theta 0. So I have this one, okay? So from this relation here, I obtain this one. That is equal to what? If I use the second relation, this one here, if I apply it for theta here equal to theta 0, I obtain 0. And I can say that theta 0 fulfills the Euler condition. And in fact, what I have written here is exactly this one. Say that theta 0 fulfills the Euler condition means this one, okay? And this one is exactly this expectation here. This expectation here, this one, so let's write it here. The expectation of the derivative of the logarithm of f x theta 0 over d theta here, yes, is equal to 0, because here it is simply what you have here is just minus infinity plus infinity d f x theta 0 over d theta dx by my previous computation, okay? And what I have here is exactly to say that I have this one here, okay? So theta 0 fulfills my Euler, my first order condition, that is the Euler condition. So just a remark here, as you see here, I have done all the computations here. I have done all the computations as if, okay, I can write it here. So, okay, suppose that theta is included in R. I do the proof, in fact, in this situation because I want to deal with partial derivatives in the proof. But in fact, if you follow what I have done, just considering partial derivative will give you exactly the same thing. Here, I just consider that, in fact, my parameter is a number that is a subset that belongs to a subset of R. But here, what I have stated, okay, is true for any type of situation, in particular, if theta is included in R to the power D. Instead of having, I will comment it at the end, instead of having this Euler condition here, you won't have to forget that this Euler condition will be, in fact, okay, several scalar conditions here. But I do the proof here for theta included in R. And I just have to compute derivatives instead of partial derivatives. Okay, so I have this one. I prove that here, this one is fulfilled for theta 0. So theta 0 And it's just, okay, an implication of the Euler condition. So second thing, if I want to check that I have a maximum, you know from the course of optimization that to check the Euler condition is not sufficient. Okay, so I have my Euler condition, and you know that if you want to check that you have a max or a mean, you have to consider the second derivative. You have to consider the second derivative. And if I want to compute the second derivative will just be the derivative of the derivative. That is this one. So maybe let's do this here. I just copy this slide here. I will put it here. I will erase what I don't need. That is now I don't need anymore all these things here. I have them in mind. And I am just interested in this quantity. Okay. And I want to compute the second derivative of my objective function. In order to obtain it, so here I have this term and this term here. Okay. If I want to compute the second derivative, I say that I have to compute the derivative of this one with respect to theta, and keeping in mind that I have the right to invert between an integral and the derivative. If I compute, okay, I will obtain what? I will obtain the integral between minus infinity and plus infinity of the derivative of this ratio here. So I have u over v. The derivative will be u prime v minus u v prime over v square. So let's do the job. Okay, so u prime, that is the derivative of the derivative, that is the second derivative with respect to theta of f x theta. So u prime v minus u v prime, and v prime is equal to this one. So I have this one, d over d theta f of x theta, and I have a square here over v square. This one, that is just, okay, this quantity multiplied by the true density function, that is this one. Okay, and keep in mind that here, you just have here the derivative with respect to theta of the derivative with respect to theta of fx theta divided by fx theta. You have this one here. Okay, so let's see what happened at theta 0, because here you have f second of theta. Okay, I want to see what happened at theta 0. So what is f second of theta 0? And keep in mind that if I want to prove that theta 0 is at least, at the very least, okay, a local maximum here, we have checked that it fulfilled the Euler condition, and then I have to check that the second derivative, okay, at the point theta 0 is strictly negative. Okay, it's the condition you have, okay, in order to ensure the existence of a local maximum here. So phi of theta 0 is given by what? So I replace the things, okay. So let's write it, okay. It's so keep in mind what happened. So I can write it this way here. So for theta, I obtain this one. And if I put theta 0, I will have theta 0 here, theta 0 here, theta 0 here, theta 0 here. Okay? And I have just, don't forget that you have here dx. So of course, I will have some simplification if I do this job, because you see that here, fx theta 0 and fx theta 0 square will simplify a little, okay? And here you have also f of x of theta 0. So you have fx theta 0 multiplied by fx theta 0 divided by fx theta 0 square. So for this first part, okay, here you have simply integral minus infinity plus infinity of the second derivative with respect to theta of fx at the point theta 0. And that's all, because this one, and this one simplify, and minus d over d theta fx theta 0, and I can put a square here of what? something that is, okay, here divided by, I have fx theta 0, I divide by fx theta 0 square here, and it remains fx theta 0 here, dx. Okay, so I have this relation here. It's what I have obtained. So computing this derivative, the derivative of this derivative, I obtain f second of theta. If I plug theta 0 inside, I obtain this one here. Okay, so let's erase this part that I don't need anymore here. And my job, I remind you that my job is to check if it is possible to prove that this one is strictly negative. And the answer is yes. Why? Because I keep in mind the following. So keep in mind that I have said that this one is equal to 1. So if you compute the derivative of this relation with respect to the plus here, okay, with respect to theta, I obtain this. Just computing the derivative, it's something that I have already used. And if I compute the other derivative, I also obtain equal to 0, because if I compute the derivative of the derivative, I obtain here as a right term, okay, at 0. So implying that, in fact, in my expression here, so if I express this one here, it is equal to what? I obtain phi second of theta 0. So from what I have done here, I obtain what? By this term, the first integral, in fact, I have two integrals, one here with, and the other one with the minus before here. The integral of this term is equal to 0 from this one. So I have 0 minus the integral between 0 minus infinity, excuse me, and plus infinity of d over d theta f of x theta 0 square over f x theta 0 dx. But what you have inside here, you have something that is a square, so you have something that is positive. You have here a density that is positive, and you have a minus before, so you have something that is strictly negative here. Okay, and since I have a second derivative, you have, okay, here a local maximum. And so you have, okay, at the very least, from the local point of view, the fact that your true parameter fulfills, in fact, the maximization program. It's the one that maximizes this quantity, the one that maximizes this quantity. And in practice, okay, a priori, in order to find theta 0, I have to solve the Euler condition. That is the first order condition when you have an optimization problem, okay? And we have proved, computing the second order condition, that it is really, at the very least, a local maximum here, because the second derivative at theta 0 is strictly negative. Okay, so you can omit this proof, okay, for the final exam, but it was just to show you that my true parameter, and something that will be fundamental for us, in fact, okay, may be related to a concrete problem that is, okay, to maximize, okay, the expectation of the logarithm of the density function, okay, at the point capital X. If I do this, I obtain theta 0 as the point where this maximum is reached, okay? And now the idea is, using this proposition, we are going to have an idea in order to approximate theta 0. So theta 0 is obtained as the maximum of some 1. The idea will be to approximate this sum 1. If I approximate my objective function, that is this one, and we are going to see how to do this just after. So if I approximate my objective function by an approximated objective function, if I found the maximum of this approximated objective function, but maybe the maximum of the approximated objective function will be a good approximation of my theta zero, that is the maximum of my real objective function. Okay, and it's exactly what we are going to do. It's exactly what we are going to do. So it's the maximum likelihood estimator. Okay, so the idea is very basic. So here, in fact, in this slide, I just introduce notations, in fact, okay? So let's do it here. So what is, so I just remind you what I have done. We have seen that the true parameter theta zero fulfills theta zero, that is the point where the maximum of this objective function is reached. We have proved it, okay? So I have done the proof in the scalar case, but we have exactly the same thing, okay, in the general case. Okay, now, so I have my objective function here. Objective function in my optimization problem. Let's approximate this objective function. This objective function is an expectation. But we have seen in the previous chapter how to approximate an expectation. If I have observation of capital X here, that I call X1 XL, the n sample, that is n independent random variables having the same distribution as capital X, I know that I can approximate the expectation using the sample mean. And what is the sample mean in this situation? The sample mean is equal to 1 over n, the sum from I equal to 1 to capital N of the logarithm of f of xi theta, where the xi, okay, are the capital N sample of my capital X. Okay, n sample of capital X. Okay, so we introduce some notation. Okay, we introduce what we call the likelihood function, that is the product, okay, of this quantity. So here you have the density of capital X at the point xi, okay. Keep in mind that here it's the real density if I am in the continuous case, okay. If I am in the discrete case, okay, you have just, it's equal to the product of the probability mass function. So let's write it this way. If you are in the discrete case here, so you have the density, the real density in the continuous case, and in the discrete case, you have, okay, the probability that X is equal to xi theta if we are in the discrete case, okay. So it's what we call the likelihood function here, the product from I equal to 1 to n of fxi of theta, and the log likelihood is just the logarithm of this quantity, the logarithm of this quantity. And what is the logarithm of this quantity? It's the logarithm of a product. So it's the sum of the logarithm. And you see that here, in fact, you have exactly using these notations, using this notation here, you have exactly what you have calligraphic L n of theta. It's what we called the log likelihood. And in fact, I see that 1 over n times the log likelihood is something that approximates my objective function having theta 0 as a maximum. And what we are going to call the maximum likelihood estimator so the maximum likelihood estimator based on this capital N observation is something that I will denote this way. Maximum likelihood estimator will be the one that will maximize this quantity. But since this one is a constant, it is sufficient to maximize this one. So it's the argmax of theta belonging to the set of the parameters of by the log likelihood based on my capital N observation. Okay. And in fact, here, okay, so you see the principle, huh? You have theta 0 that is the max of this one that may be approximating using the log likelihood, and I expect that the value that maximize the log likelihood, okay, since the log likelihood, okay, is an approximation of this one, will be a good approximation of my parameter of interest, okay? So it's that natural. Theta 0 expressed as a maximization program. I approximate this maximization program, okay? I obtain a maximum in this approximated optimization program. That is what I call the maximum likelihood estimator. And then I hope that this estimator will be a good approximation of theta 0. And it's what we are going to see later on. In fact, that this is the case. Okay, that this is the case. And in particular, okay, so my maximum likelihood estimator is the maximum of this quantity. From what you know from the course of optimization, if you want to find a maximum, you will have to solve the Euler condition, and meaning that it's exactly what you have here. So keep in mind that theta ml of E, okay, maximum likelihood estimator is the argmax theta belonging to capital theta of what? Of the log likelihood. That is just the sum from I equal to 1 to n of the logarithm of f of xi theta. Okay, so it's the maximum of this objective function. If I want to find it, I have to solve. It's the Euler conditions. Okay. And what are the Euler conditions? It's just that I have to compute the derivative of this quantity, that I can express this way. Okay. And just be careful because here, in fact, it has to close the parentheses this way here. So, excuse me, we'll use the same color. Here, this one, okay. So the sum of the derivative with respect to theta of the logarithm of the density function at the point xi, it's what I will denote by zx capital theta, z capital X theta, and it's something that we call the score. The score function is just the mapping that I have to make equal to 0 in order to solve the Euler condition in the previous approximated, okay, optimization program. Okay, and just have a look, and we are going to see an example just after. Here, keep in mind that this first order condition, okay, if theta is included to r to the power d, I have in fact d partial derivatives. So I have, okay, d equations. So I will have the sum from I equal to 1 to n d over d theta 1, the logarithm of f of xi theta equal to 0 until the sum from I equal to 1 to n, okay, d over d theta d here, logarithm of fxi theta. Okay, so Euler conditions, it's just a single equation in the case where my parameter is a real number. but will be, okay, a set of D equations in the case where my parameter is a vector, okay? So I have this one. It's the classical way. And I can write it in this short way, having in mind that this is what we call the gradient of this mapping, okay? So that is the vector of the partial derivatives. So maybe, so to conclude the first part of this session, okay, we are going to see an example that is related to the Gaussian distribution. An example that is related to the Gaussian distribution. Maybe let's do it here. Let's do it here. Okay, so suppose that we are in the following situation. Okay, so I have my X that follows the n mu 0 sigma 0 square. Okay, so I have two parameters of interest, that is mu 0 and sigma 0 square. I don't know them. Okay, I don't know them. The only thing I know is that, okay, I depend on two parameters belonging to this set of parameters. Okay, and I have x1, xn, the n sample. And I want to approximate my mu 0 sigma 0 square, okay, from my hypothesis, that is that I know that I belong to a Gaussian family. Okay, I know that I belong to a Gaussian family, but I don't know, okay, keep in mind that mu 0 and sigma 0 square are unknown. Okay, it's important to have this in mind. I don't know them, I want to approximate. But what I know is that okay, I know that the density of, okay, interest here, something of this form, it depends on mu and sigma square, okay, with my notation, and is given by 1 over the square root of 2 pi sigma square exponential minus x minus mu square over 2 sigma square. Okay. Okay, so if I want to compute or to find explicitly the maximum likelihood estimator, I have, okay, to find the point that maximizes the log likelihood, and remind that the log likelihood defined previously. So if I denote this one by theta, okay, this vectorial parameter, ln of theta here is what? Is the sum from I equal to 1 to capital N of f, excuse me, so I have here the logarithm of f of xi, let's say theta here. And what is this one? It's the sum from I equal 1 to n of what? So the logarithm of this quantity here, the logarithm of this quantity. Okay, so I have the logarithm of a product here, that will be the sum of the logarithm. I have 1 over the square root. So for this first term, if I take the logarithm of this first term, yeah, I obtain what? I obtain minus 1/2 the logarithm of 2 pi sigma square. That is the logarithm of this expression here, using the properties of the logarithm. The logarithm of 1 over some 1 is minus the logarithm, and the logarithm of some 1 to the power alpha is alpha times the logarithm. So I obtain this one, and then I obtain the logarithm of the exponential, that is just minus xi minus mu square over 2 sigma square. Okay, so I can write it this way. Here you have a sum with n terms, okay, but here I have constants, so I obtain minus n over 2, the logarithm of 2 pi sigma square, and then here I have minus the sum from I equal to 1 to n of xi minus mu square over 2 sigma square. Okay, so you have here the log likelihood in the Gaussian case, so something that you have to be able to compute very quickly for the final exam, okay, because it's a classical situation here. I compute the log likelihood in the Gaussian case, and I obtain exactly this. Okay, so now, if I want to solve the first order Euler condition, what I have to do? I have to compute what I have called the score, that is, okay, but the derivatives, the partial derivatives of the log likelihood with respect to the parameter of interest. So let's erase this one. And from this relation here, from this relation, I deduce that. So I have two parameters of interest, and my theta is equal to mu and sigma square. So my parameters of interest are mu and sigma square. Okay, so be careful because here my parameter of interest is sigma square. It's not sigma. Okay, so sigma square is my parameter of interest. So first, I have to compute the partial derivative of the log likelihood with respect to mu. So what I obtain if I do this, okay, so you have to compute the derivative with respect to mu of this quantity. Here you will obtain 0 for this quantity, and you will have just to compute the derivative of this one with respect to mu. And I will obtain, if I do this, okay, I obtain 2 times the one that comes from the derivative of the square here, the sum from I equal to 1 to capital N, okay, of what? Of xi minus mu over 2 sigma square. That is something that I can express this way if I want to express it in a shorter way. So first I see that I can simplify the sigma square, and I have 2 terms in my sum. Okay, so it is 1 over sigma square that I can remove, okay, time what? But the sum of the xi that I can write xn over line multiplied by capital N. It's capital N times the simple mean because it's the sum, okay, so I multiply by the number of observation minus capital N mu here, okay? So I can express it in this compact way here. In the same way, if I compute here the derivative of the log likelihood with respect to sigma square, so keep in mind that my parameter of interest here is sigma square. It's like, okay, sigma square is equal to x in the expression, okay? So I have to compute this one, that is the constant multiplied by the logarithm of 2 pi, let's say my parameter of interest, okay? So I have to compute the derivative of a logarithm, and I obtain simply minus, okay, n over 2 sigma square, because the derivative of the logarithm of x is equal to 1 over x. So I obtain this one. And then I have to compute the derivative of 1 over sigma square, okay? The derivative of 1 over sigma square, that is, if you want the derivative of 1 over x, the derivative of 1 over x being minus 1 over x squared, I obtain here plus, okay, the sum from I equal to 1 to n of xi minus mu square over 2 by sigma square square, that is 2 sigma 4. Okay, so you have the log likelihood here. You compute, so you have the log likelihood expressed this way. Okay, I compute the partial derivative to obtain this quantity, what I have called the score. First, the partial derivative with respect to the first parameter, that is mu. I obtain this expression, and then the partial derivative with respect to sigma square, the parameter sigma square, and I obtain this quantity here. And now, if I want to find the maximum likelihood estimator, I have to solve the first order condition, that is the Euler condition. And what is the Euler condition in this situation? Okay, so I erase this one now that I don't need because I have used it in order to compute the score, that is the vector of the partial derivatives. And I want okay, to make, so the Euler condition, I have two Euler conditions here because I have two parameters. The first one is 1 over sigma square n xn over line minus n mu at is equal to 0, because I want the point where this one, so excuse me, I have also sigma square at here, okay? Because, okay, the Euler condition is just, okay, I can write it this way, d over d theta ln of theta at is equal to 0. Huh? This is my Euler condition, expressed this way here, okay? It's the one that fulfills this one. So I replace mu and sigma square by the point where 0 in the Euler conditions, and I obtain here the second one, that is minus n over 2 sigma square at plus the sum from I equal to 1 to n of xi minus mu at square over 2 sigma at 4 equal to 0. And here it's not that complicated to solve. I have a system of two equations with two unknowns, the unknowns being mu at and sigma at square. So from this equation here, I simply find that mu at is equal to xn over line. And if I plug inside mu at, okay, that I have obtained from the first equation in this one here, I simply obtain, okay, what? But that is sigma n, or I can write it this way, excuse me. And I obtain that sigma at square is equal to what? But it will be simply 1 over n, the sum from I equal to 1 to n of xi minus mu at, that is minus xn over line square. So you obtain for mu at here the sample mean. You obtain for mu at square the sample variance. So in the case of a Gaussian distribution, the maximum likelihood of mean and the variance is what? Is simply the pair sample mean, sample variance. So in the case of a Gaussian distribution, in order to approximate mu and sigma square using the methodology we have seen now, that is computing maximum likelihood estimators, we obtain simply for the pair mu sigma square, the sample mean and the sample variance. Okay, so in order just to finish, let's keep in mind that we have done things concerning the sample mean and the sample variance. Okay, so what can I say? So I have mu, that is the sample mean, and sigma square, that is the sample variance. So what I know for these two estimators, so I have solved the thing, so I have everything here. So what I know for this estimator, so what I have done from the previous chapter, so from the previous chapter, what I know, but I know what is the expectation of mu at. It is mu, because I know that the sample mean is unbiased. I know that the expectation of sigma at square, here the sample variance, I know that it is biased, n minus 1 over n. Okay, so excuse me. So here the expectation of mu at, okay, that is, okay, when it's mu 0, the true parameter that I obtain here. Expectation of sigma at square is n minus 1 over n sigma 0 square. Mu 0 and sigma 0 being, so here you have something that is unbiased, we know. And we know also that if I want to compute the mean square error in the case of mu hat is just the variance of the sample mean that I know, that is equal to sigma 0 square over n. And if I want to find the mean square error of sigma hat square, so since I have an MBS estimator, okay, it's not only the variance, it's the variance plus the square of the bias, but I can also compute the variance of sigma hat square, and here it's the mean square error, not in the other case. What is this one? So be careful because, okay, a priori you don't have the formula in the course, okay, but I just have the following one, okay. So here you have the sample variance, okay, and I know that the corrected sample variance is defined as, okay, this one, n over n minus 1 sigma square hat. Here I have defined the corrected sample variance this way, and I know what is the variance of the corrected sample variance. So it is n minus 1 over n square time the variance of the corrected sample variance, because you have in the course, in the previous chapter, okay, and at the beginning of this one, what is the variance of the corrected sample variance? I give you the formula. So I have here n minus 1 over n square, and I have a formula that I have reminded at the beginning of this section, that is 2 sigma 0 to the power 4 over n minus 1 plus mu 0, 4, that is the centered force order moment for the situation here, minus 3 sigma 0, 4 over n. But we are in the Gaussian situation, and for a Gaussian random variable, okay, you have mu 0, 4, in fact, for a Gaussian random variable that is equal to 3 sigma 0 to the power 4. So for the Gaussian case, this one is equal to 0 because we have this in the Gaussian case. So you have, okay, this expression for the variance of the sample variance in this situation, okay, that I am able to compute from the fact that I know variance of the corrected sample variance with this link between the variance and the corrected sample variance. Okay, so in the case of the Gaussian, when I am interested in the two parameters related to this distribution, that is the parameter mu and the parameter sigma square, that are in fact the mean and the variance, the maximum likelihood estimator that I have obtained by my computations are simply the sample mean and the sample variance, okay? And it's possible for me to study their properties because in this situation, okay, I know from the previous chapter what are the properties of this estimator, okay? So I will stop the first video here, okay? And I will continue in a second video in order to show you that in the framework of the likelihood problem, okay, we are going to be able to find optimal criteria for MBS estimator. That is, to be able to say if you have an MBS estimator, to be able to say if it is optimal or not. That is, if it has the minimal mean square error in the situation. So it's what we are going to do in the next video. So see you.